Alright guys, so this is our final video on the polar coordinate system, or the polar plane. And in this video we are going to talk about graphing polar functions, or polar equations. Now the points for these polar equations are going to be defined by inputs of the directed angle theta and outputs of r values, the directed distance, right? So right here, looking at our first example, we've got r equals 2 sine theta. And what we want to think here is that 2 sine theta is going to evaluate theta values and give us r values in the exact same way that the sine wave 2 sine x evaluates x values and gives us y values. So really what we're going to see here is that we get the same ordered pairs for y equals 2 sine x that we do for r equals 2 sine theta. And the difference is really going to be how we graph these ordered pairs, or how we interpret the ordered pairs with regards to position. So right here what we're going to do is plug in a collection of theta values and get some r values, and then we'll plot the ordered pairs on the polar plane. And then we're going to talk a little bit about the relationship between these two guys. So right here, let's say we've got the rotation of 0, the rotation of pi over 4, the rotation of pi over 2, the rotation of 3/4 pi, and the rotation of pi. So right here, plugging in 0, sine evaluates 0 and gives us an output of 0 times 2 would be 0. Plugging in pi over 4, we get square root of 2 over 2 for sine, and then we multiply by 2, and that gives us the square root of 2, and when we evaluate that square root of 2, that's approximately 1.4. When we plug in pi over 2 into sine, we get an output of 1, times 2 would give us 2. We plug in 3/4 pi, that's again square root of 2 over 2, multiplied by 2 just gives us square root of 2, and right here when we evaluate square root of 2, we get approximately 1.4 again. When we plug in pi, we get an output of 0 from sine, so 2 times 0 is 0. So here we have a collection of ordered pairs, and what we want to do is graph them on the polar plane. So what we're talking about here are rotations and then distance in those rotations. All of our r values are positive, so what we're going to see is basically us moving the length of that r value in the direction theta that we rotate to. So first we've got a rotation of 0 and an r value of 0, so that pretty much lands us right on the pole, right on the origin. Then we've got a rotation of pi over 4, so that's this amount of rotation right here. And we are talking about going out a distance of 1.4, which is almost 1.5. We can sort of approximate there till we get that point. Now we rotate to pi over 2, and we're talking about an r value of 2, so we would go a distance of 2 in that direction. Now we rotate to 3/4 pi, which is approximately this amount of rotation, and as an output for that rotation we're seeing 1.4, so again that's almost 1.5, it gives us that point right there. And then finally for a rotation of pi, we are seeing an output of 0 again, so that lands us right back on the pole. So again, what we've done is talked about a couple of rotations on the interval of rotations from 0 to pi, and plotted those rotations and those r values for our polar coordinates right there. So right here we've got a collection of points on our polar plane now, and what we want to think is, what is the progression of r values across that amount of rotation, right? What's happening as we progress through that the rotation of 0 to pi? What's happening with our r values? And what we can think is, what's happening with our r values for our polar function is the same thing that's happening with the y values for our sine wave. So right here we start out with a y value of 0, seeing the same thing right here, and then those y values get steadily greater until we get to pi over 2, and then they reach their maximum value right there, and then they get smaller and smaller as we go back to pi. So right here, as I go over to my polar graph, what I want to think is I've got r values extending to points as I rotate through these first two quadrants, starting very small, then getting longer and longer, extending all the way out to 1.4, continuing to get longer, as they extend out to R2, and then they start to get shorter and shorter. So I'm extending out to points that are less and less distance away from the origin to 1.4, and then shorter and shorter distances all the way back to 0. And what we're seeing right here is basically a collection of ordered pairs at the ends of those R values that create a circle. And we can see this if we go to our calculator and graph this function on our polar plane. So right here, taking out our calculator, we can go to mode and then down to function. Function is us basically graphing on the XY axis. We've got a way to graph on the parametric axis right there, and then going over one more, we're seeing polar, and when we press enter and highlight that, now we're going to be graphing on the polar axis, or the polar coordinate system. So right here, going to y equals, now we'll see outputs of r values, and our x button that normally gives us the input of x is going to give us the input of theta value. So right here, we can type in 2 sine theta, and close our parentheses, and when we graph this guy, we're going to see that circle, right? Now it looks a little more like an oval because the scale is slightly off between our y and our x axis here. But in general, we're seeing the same graph that we just created with our r values right there. Now, what I want to do right now is talk a little bit about what's going to happen as we rotate through the third and fourth quadrants. So right here, let's talk about plugging in theta values from pi to 2 pi. So we're talking about pi. We could plug in 5/4 pi. We could plug in 3/2 pi. We could plug in 7/4 pi, and finally 2 pi, right? And these are going to be rotations through our third and fourth quadrant. So right here, plugging in pi, we of course get 0. Plugging in 5/4 pi, we get negative square root of 2 over 2, which when we multiply by 2 gives us negative square root of 2. And when we evaluate that, that's approximately 1.4. When we plug in 3/2 pi, we get negative 1, so that's going to give us an output or an r value of negative 2. Plugging in 7/4 pi is again negative square root of 2 over 2, so times 2 would give us just negative square root of 2. And when we evaluate that, we get negative 1.4. And then finally, plugging in 2 pi gives us an output of 0, so 2 times 0 gives us 0. And those are the corresponding r values for the rotations we plugged in. Now right here, what we want to think is we're actually seeing negative r values. And what does that mean? That means that we're going to be going in the opposite direction to define our point. So right here, as we rotate through the third and the fourth quadrant, we're actually going backwards with our r values. And so really what we're seeing is us going back over the same points on the perimeter of the circle that we just defined, right? And you can see this on the graph of y equals sine of 2x as well. When we rotate from pi to 2 pi, really what we're seeing here is those same outputs, only negative, right? So basically, it's those same outputs, and when r is negative, that means we're going in the opposite direction, and we're sort of hitting all of the ordered pairs that created that circle again, right? Now, what we're going to talk about at this point is a way for us to represent our polar function as a rectangular function, or as a function we would graph on the xy axis. And what we're looking to do here is take our r and our sine theta and represent them with x and y values. So when we're talking about rotations from standard position, we've said that the distance from which we evaluate an x and a y value on our terminal side to give us the ratios of sine and cosine, we say that that distance is a distance r, right? So right here, we've said that with the Pythagorean theorem, we can define that distance as the square root of x squared plus y squared. Now right here, if we, and of course that distance is a distance from the origin to a certain point on the terminal end of a rotation. So right here, if we square both sides, what we get is r squared equals x squared plus y squared. Now we've got a relationship between an r squared and just x and y squared, right? Similarly, when we're talking about rotations from standard position, we say that cosine of theta is x over r, and sine of theta is y over r. So if we want to define cosine as just an x, we can multiply by r on both sides, and we would get x equals r cosine theta. And similarly, we could multiply by r on both sides for our definition of sine, and get y equals r sine theta. Now right here, what we're going to look to do with our polar function is to substitute for r and sine theta with our relationships that we're seeing over here. So right here, immediately we don't have r squared, but if we multiply r on both sides, we can get r squared equals 2r sine theta, right? Now, we've got a relationship that tells us that r sine theta is equal to y, and r squared is equal to x squared plus y squared. So right here, we can go ahead and substitute in, and we'll get x squared plus y squared for our r squared, and 2y for our r sine theta. Now, at this point, this doesn't look much like the equation for a circle that we recognize, but we can do some algebraic manipulation and get it there. Right here, if we subtract 2y from both sides, we get x squared plus y squared minus 2y equals 0. And then if we add 1 to both sides, we can then factor out our y squared minus 2y plus 1 and get x squared plus, and then y minus 1 times y minus 1 equals 1. Now right here what we have is x squared plus y minus 1 squared equals 1. And this is the equation for a circle, where we have x minus h squared plus y minus k squared equal to r squared, where hk is the center of the circle. So what we're seeing right here is a circle with center 0, 1, and radius 1. Now, if we were to go up to our polar, the graph of our polar function right here, what we're seeing is a circle whose center is at 0, 1. And if we draw a line from the center of that circle to the perimeter, we can see that the r value here is also 1. Right? So we've got that same graph. We would have the same graph right here for our, for the equation of the circle we got by substituting. Okay, so we are going to go ahead and talk a little bit about graphing some of these, some of the other kinds of polar functions that we're going to see. Right here, in general, what we're going to do is the same thing we did before. We're going to plug in, theta values in increments of fourths of pi for a full rotation. And that's going to give us a collection of ordered pairs that we can graph on our polar plane, right? Now later we're going to use different points and some properties we're going to determine of these functions. But for right now, what we're going to do is just plug in these theta values and get some r values and plot the ordered pairs, and so to see what kind of graphs we're getting from some of the equations we've got for our polar functions. So right here, we've got our polar function r equals 1 minus 2 cosine theta. And when we start to plug in values, we can start to get some outputs. When I plug in 0, cosine equals 1, so 1 minus 2 is going to give me negative 1. When I plug in pi over 4, I get approximately negative 0.4. When I plug in pi over 2, I get 0 for cosine, so I get an output of 1, or an R value of 1 there. When I plug in 3/4 pi, I'm going to get 2.4 approximately. Plugging in pi gives me -1 for cosine. So right here, -1 times a -2 gives me a +2, and that's going to give me a value of 3. When I plug in 5 pi over 4, I get 2.4 as my output. And plugging in 3/2 pi gives me, of course, a cosine value of 0. So, of course, again, that would be 1. And then 7/4 pi is going to give me -0.4 again. And then plugging in 2 pi is going to give me an output of 1, so I get -1 as my output. And again, what I'm doing here is just basically taking these theta values, plugging them in here. I could plug them into the calculator. That's basically what I'm doing. And I'm rounding them pretty heavily because I'm not going to get exact values. But let's go ahead and plot these ordered pairs. So right here, we've got the ordered pair 0, 1. So for a rotation of 0, 0, -1. So for a rotation of 0, we have an R value of -1, which means we're going -1, right? We're going in the opposite direction. For an R value of pi over 4, we've got a -0.4, so that's almost -0.5 right there. For an for a rotation of pi over 2, we've got an R value of 1. So now at this rotation, we start traveling in the direction of that rotation because we've got a positive R value. For a rotation of 3/4 pi, we've got an output of 2.4. So that's going to be approximately 2.5 right there. Right here for an R value of pi, we've got an output of 3. So again, what I want to think is this is the direction I'm going in, and I'm traveling a positive 3 units in that direction. So that takes me out to this point right here, right? Now right here for 5/4 pi, that's this amount of rotation. I've got 2.4, so that's approximately 2.5 units in that direction. And for 3/2 pi, we have, again, 1, so 3/2 is a rotation that takes us down here, and we go a length of 1 in that direction. Now right here for -0.4, for 7/4 pi, rotation of 7/4 pi, we've got a -0.4, so I'm going to go in the opposite direction, 0.4. And then for 2 pi, I've got that value of 1 again. So right here, what I'm going to do is connect all of these ordered pairs in order. So right here, I'm going to see a graph that looks like this. Approximately like this. Now, at this point, what I would point out is, we're going to use ordered pairs differently to get easier graphs to get more accurate graphs later. But right here, this is a pretty decent graph for what I've done. And if we think about this with relationship to the graph of y equals 1 minus 2 cosine x, right here we would say that this is the graph that has the equilibrium line of +1. It's a negative cosine, so it's going to start at its min, and we can say that the amplitude is 2, so I'm going down 2 units, and then halfway through my period, I would be up at my max, and then right here, I'd end my period down at my min, and I'd look something like this. Now think about the outputs we're getting here for this graph. So we start out with negative outputs, then we get 0, then we get positive outputs, then we get 0, and then we get negative outputs again. And basically what we're sort of seeing here is we start out with negative R values, so R values going in the opposite direction, then they become positive, and then we get negative R values again. So what I want you guys to do right here is go ahead and find these ordered pairs and then plot the ordered pairs on the polar axis, and then try to connect them in order. All right, so pause the video and give this a shot. Okay, so we've plugged all our theta values into our function r equals 2 plus 2 sine theta, and we get these sets of r values, which we can then graph with the theta values to give us these polar coordinates. Right here we start out at 2, and then we basically just want to go and connect all these ordered pairs. So we look like this. And that should be an approximate graph of our polar function. So again, right here, we'll talk more about graphing these on Wednesday. I'm going to try to make that first video shorter. We'll see. But in general, right here, the way we want to think about graphing these is basically just plugging in those values for those theta values into our function, getting r values, and then plotting those ordered pairs, right? And we'll talk a little bit more about some shortcuts in graphing on Thursday and maybe even Friday. All right, guys, so that's our video. We are done for tonight, and I will see you guys on Thursday. All right.